name is Abby White. I'm the project manager and structural engineer for the OKAE engineering team. With me today are the other talented members of the OKAE engineering design team. We have Katie Schreiner, transportation engineer, Ellen McCulley, our water resource engineer, and Olivia Holtz, our environmental engineer. And today we're excited to present to you our current progress report for phase 2 portion of the Amazon Industrial Park project. To give a quick project overview, we'll be designing a new Amazon warehouse facility, as well as a new connector road from County Road 17 to County Road 19. We will also be implementing stormwater management practices to prevent flooding and to reduce potential pollutants. And we'll be designing a new wastewater treatment facility to reduce contaminants before discharge. And to give a quick structural project scope, the structural department will be designing a new Amazon warehouse facility of approximately 48,000 square feet, and it will include spaces for office and reception use, warehouse storage, packing and shipping areas, equipment storage, and auxiliary spaces. And currently, we have been working on the preliminary design, the preliminary member classification, RESA design, load calculation, and staying compliant with local building codes and regulations. And this image shows the location of the warehouse. To give a quick update on the structure, we have adjusted some of the square footage. So it is still a one-story steel structure, has the same type of designated areas, but the area is now 48,000 square feet. As in the previous presentation, it was 50,000 square feet. We have adjusted this and lost about 2,000 square feet due to making the building more uniform for the structural framework layout. This eases the complexity of the design for the engineer, of myself, as well as the construction. Here is the warehouse structural framework layout. This is the finalized plan. You can see here that we'll be using W-shaped beams and columns, and for the braced elements we'll be using channels. In the colorful area on this image, that is the warehouse structural framework. It's sitting at an elevation of 35 feet, and I did not include the office area because that's sitting at a different elevation. In here you can see in the north side and the south side there are 4 green boxes. Those are the braced elements that help protect against any lateral loads. In addition to this, we will be including 3 rows or columns of moment frames, and they're sitting at all the way at the west end of the building, the east end, and right in the middle, approximately around this line right here. And a combination of those, the moment frames and the brace frames, will help protect against any lateral loads and provide stability to the building. And here's the office structural framework layout. It's essentially the same thing as the warehouse, but is sitting at an elevation of 20 feet. Here are the west and north elevation wall plans. You can see here this is where the moment frames and brace frames come into play. Along the west wall we'll have moment frames, and along the north wall we'll have gravity frames and brace frames. The combination of these two will protect against lateral loads. And here are the east and south elevation wall plans. They kind of have a similar type of thing going from the west and the north. But the difference here is these walls go into the office, so the height of the walls have changed, as you can see, all the way to the right ends of the image. It has narrowed down to 20 feet instead of 35 feet, but they will also be including moment and gravity frames as well. And here are the north and west office elevation plans. To give a quick note, these are the walls that will be connecting the office and warehouse together. So they're sitting at an elevation of 35 feet because they will be having the warehouse with them. And then they'll be on the other side, it'll be 20 feet. And they'll be using gravity frames. So here are the load summary tables that we have found to help calculate the wind and snow loads that will be used in the next slide. And here is our calculated flat snow load calculation. We've taken this from the ASCE hazard tool and the ASCE. You can see that the calculated number is 18.9 PSF, although there are some ASCE requirements that the minimum amount that you can have is 20, so we'll be using 20 going forward, 20 PSF. And then for the wind load, we had to calculate 2 different wind pressures because of the different elevations in the office and the warehouse. So for the office, it's about 24.7 PSF. In the warehouse, it's about 27.7 PSF. We'll be continuing with doing the snow drift calculations, as well as continuing to do other calculations for the wind load. So this is the table for the preliminary memory summary table. Again, it's important to note that these are preliminary numbers. We are currently working on the RESA design to help determine the final selection of the members, but I don't have solid numbers to be able to give you guys that. So these are subject to change and will change pretty soon here. And for the future work, kind of piggyback off the last slide, we'll be completing the RESA design, which includes RESA 3D and RESA floor, as well as the column design, foundation design, and connection design, and as well as any additional structural items that would be needed to be designed for this facility, as well as the construction cost estimate. And now I'd like to pass the torch on to Katie to talk about the transportation project.
Hi guys, my name is Katie and I'm the transportation engineer with OKAE Engineering. I'd like to start by reviewing my transportation scope for this project. As Abby said earlier, I was tasked with the development of the County Road 4 expansion, which will provide access to the warehouse that's going to be constructed on the eastern end of the site. I'm also in charge of the development of any and all parking structures relevant to the site, and all of these items will be designed in accordance with the Indiana Design Manual, the AASHTO Green Book, Elkhart County Codes and Regulations, and the Americans with Disabilities Act. This is the current alignment of the County Road 4 expansion. You'll notice that it is lined up with the existing infrastructure on County Road 17 and County Road 19. On the western half of the site, we did our best to utilize as much of the existing roadways as possible in hopes of reducing the construction costs that were estimated in phase 1 of this project. The design criteria, the County Road 4 has a 45-mile-an-hour design speed with a lane width of 12 feet, and it will have a horizontal curve of 715 feet. The Indiana Toll Road entrance has a design speed of 30 miles an hour, lane width of 12 feet, and a minimum horizontal radius of 375 feet. These numbers are taken from the low-speed urban table instead of the traditional highway horizontal radius table, in the hopes of keeping speeds lower since there's a high anticipated number of truck traffic on this site. Here is a typical section for the roadway. The travel lanes, as I mentioned earlier, are all 12 feet wide with a 2% cross slope. The shoulders are 10 feet wide with a 5% cross slope. And the foreslope and back slope have a slope ratio of 3:1, meaning for every 3 feet of lateral distance, it'll go down by 1 foot. These numbers are still being calculated and as we evaluate the necessary clear zone distance and the anticipated rainfall, which I'm still working with our water resources engineer to determine. And then below is our HMA mixture that was designed in phase 1 of this project. Moving on to intersection design. These intersections are have the design vehicle of a WV67. So all the turning radiuses must be able to accommodate this vehicle. Both intersections on this site have 90-degree turns, or approximately 90-degree turns, so we need a 125-foot turn for the edge of the travelway. Starting at the County Road 4 and Indiana Toll Road entrance, you can see that 125 radius curve for the edge of the travel lane. I know it's kind of hard to see, but then there's a black dashed line that indicates the the edge of the pavement. The northbound County Road 4 lane has one left turn lane and one through lane. The southbound leg has one right turn lane and then one combined through and right turn lane. And the Indiana Toll Road lane has two left turn lanes and one right turn lane. And this intersection will be signalized. The County Road 4 and County Road 19 intersection is a stop-controlled intersection. County Road 4 will be a side street stop, and County Road 19 will be in free flow. County Road 19 is outside the purview of the scope, so there will be little to no adjustments to that roadway. Again, you can see that 125-foot radius, along with the taper distances marked on the image as well. The parking lot for this site has the car parking lot on the southern end of the warehouse and the truck parking lot to the northern side of the warehouse. There are 35 car stalls, 4 handicap stalls, 30 truck stalls, and 6 loading and unloading bays. Getting a closer look at these parking structures, the car parking lot has bays that are 20 feet by 10 feet, along with a 6-foot sidewalk on the north side of the parking lot to connect the parking structure to the main entrance of the warehouse. And then in the back of the truck parking area, stalls are 12 feet by 80 feet, which is the same for the loading and unloading bays as well. You'll see a hashed area just outside of the warehouse, which denotes the back entrance to the warehouse, so that way people can enter from that side of the building as well. Future work includes the development of parking lot drainage, determining the slope to make sure all water gets off the site, adjusting the vertical alignment of the County Road 4 roadway, and adjusting the ditch dimensions, which I have mentioned earlier. I also need to review the stopping site distances, especially with that one turn on the Indiana Toll Road entrance so close to the intersection. I need to develop a construction detour plan and develop the cost estimate. At this time, I'd like to pass the presentation off to our water resources engineer.
Hello everyone, I'm Ellie, I'm the water resources engineer for this project. I want to quickly go over the water resources scope, just reminding us all that we are hoping to manage the stormwater on our Amazon Industrial Facility site by minimizing stormwater runoff to control flooding and treating stormwater by retaining 80% of total solids and 65% of total phosphorus. This will all be done in compliance with local and state regulations. This includes the Elkhart County Street Standards and the Indiana Stormwater Quality Manual, and this will be supplemented with the Minnesota Stormwater Manual. So first, let's review the selected alternative from last semester. We have several stormwater BMPs that are meant to accommodate our flood control and water quality volume standards. We have a detention pond to contain that flood control volume, vegetative swales for conveyance and for water quality treatment, a permeable pavement parking lot, a rain garden, and a iron enhanced sand filter. These are all considered to be quite a conservative design, and we expect this to well exceed our flood control and water quality volume expectations. So here's just a quick overview of the site. We have those vegetative swales along the roadways that will convey our water down to our site location. Most of the water will be entering through the rain garden, the sand filter, and into the detention pond, with some of it coming off of the building and the parking lot and going straight, that permeable pavement parking lot, and going straight into the detention pond. Next, we have a few design criteria to review. First, after reviewing much of the regulations, I just want to note that a lot of the stormwater BMPs will be assumed to have a 3-to-1 side slope, a 3-to-1 length to width ratio, and a 24-hour drainage time. This is pretty standard across all of our regulations that I've found, so just want to go ahead and put that out there, that would be considered the standard unless otherwise noted. So something to mention for the detention pond is that instead of a 1-foot freeboard, we're going to have a 1.5-foot freeboard. And then much to do with the detention pond is what we want to make sure we're controlling the amount of water going in and the flow of the water coming out. For that, we will have the 100-year, 24-hour storage storm used to calculate that peak inflow storage. And then for the maximum allowable release rate, we will be using the 10-year undeveloped rate. Next, for the rain garden is allowed to be 3 to 12-foot basin. However, it is recommended that it will use shallower gardens with high surface areas. And this will be later discussed as we get a little bit further into the rain garden design. This will have a 6-hour drainage time, and instead of a 3-to-1 side slope, we will be using a 4-to-1 side slope as recommended. And then sand filter. The Indiana State government recommends using an Austin filter for large drainage areas with commercial use. However, instead we'll be using the Minnesota filter. The difference in this is the Austin filter is considered to be a bit of an overdesign when put in combination with all of our other BMPs. It has a little bit more of a built-up framework with a sedimentation basin involved, but the Minnesota filter is a bit more simplistic and will do plenty to handle the loads that we need, considering we have all of these BMPs in succession. So we'll have a 5% iron by weight in the sand and a maximum 48-hour drainage time, and an underdrain of corrugated polyethylene with slits. Next, we have the permeable pavement. This will be a pervious concrete system, which has been recommended for heavy truck traffic. It will have 2 to 5% surface slopes, a minimum 6-inch reservoir depth, and a 24 to 48-hour drainage time instead of just 24. And then the concrete depth will be between 4 and 6 inches. And then finally, with the vegetative swales, we have a maximum of 1.5 feet per second runoff velocity, and we will have trapezoidal cross sections, a 2 to 8 foot channel bottom, and then 1.2% swale slopes, and a maximum 10-minute conveyance time. Let's get a bit into our rain garden design. So first, our size or geometric requirements. With that selected 1.5 foot ponding depth, we will be required to have a 23,000 square foot area. This, with the 3-to-1 length to width ratio and the 4-to-1 slide slope, means we will have a 90 by 270 bed with a total 3-foot depth to allow for some freeboard with those 4-to-1 side slopes. And then for media requirements, our ultimate goal is to retain phosphorus. And so we will have a 3-foot bioretention soil media type C as recommended by the Minnesota Stormwater Quality Manual. And this will be made of 85% sand, 10% fines, and 5% organic matter. This is highly recommended specifically for dissolved phosphorus reduction. Next, getting into our sand filter. For the size requirements, we will have a filter area of 7,500 square feet. This is assuming that 3-to-1 length to width ratio and 3-to-1 side slope. This will result in a 50 by 150 foot sand bed, and the outlet height will be 4 foot from the sand media. For our hydraulic requirements, we also made sure that using hydraulic conductivity and the above sizing, that we are still able to get down in the detention time necessary, but ultimately the geometric constraints we're controlling in terms of the size of the filter. For future work, I will be completing the detention pond design, permeable pavement design, and vegetative swale design, and continuing working on those, and then finally CAD plan development. Next, I'd like to pass it off to Olivia for an environmental.
Thank you, Abby. So as mentioned, I am the environmental team lead for OKAE Engineering. Just a recap of the scope for this project. I am designing a wastewater treatment facility for this warehouse, and it is going to be able to manage an average flow of 1 million gallons per day. And the scope also includes completing the components of each part of the treatment train process. So that includes pre-treatment all the way up to secondary treatment. So currently I have just been developing the treatment train components and designing all of them based in accordance with the Water and Wastewater Engineering Design Principles and Practices textbook from Davis. That has been what I've been using as my main source of reference, and then also making sure that I'm in compliance with all codes and ordinances as well. So this is just a schematic of the typical wastewater treatment train. As you can see, I have put a box around the pre-treatment, primary treatment, and secondary treatment aspects of this treatment train. That is because tertiary treatment is out of the scope of my project, so I will not be looking into that, but otherwise everything else will be getting developed. So to start, I want to talk about the partial flume that I've designed. The average flow in metric is 3,785 meters cubed per day, and I have selected a peak hourly flow factor of 4.5 and a minimum day flow factor of 0.35. So that gets a peak flow rate of 710 meters cubed per hour and a minimum flow rate of 55 meters cubed per hour. And then using table 23 off to the side here, I was able to determine what the throat width would be. So the 50 and 1630 are boxed because that is the minimum, and then the maximum, we don't want to exceed the maximum flow rate, so that's why I didn't choose the 520. I had to go up one, which then got me a flume width of 0.3 meters. And then using equation 20-1 from that textbook, I was able to find that the water depth is 0.22 meters, and then from that the plume depth is that water depth plus freeboard, and the standard for freeboard is 0.6 meters, so you just add those two together and it got me a depth of 0.82 meters, which I'll be using. And then this is just a schematic to see how the partial flume will be designed, and just a reminder that the throat width is 0.3 meters and the depth is 0.82 meters. Next is the bar racks. So then with the assumptions, I have that the bar width is going to be 15 millimeters for each, and then the spacing between is 25 millimeters. That's based on one of the tables from the textbook and just some of the regular kind of standards that I was selected. So that goes to have a total number of 16 bars and then 17 spaces in this bar rack system. And then the effective area would be the number of spaces times the spacing between, and then times the depth of bar rack. So it'll be 0.565 meters squared as the effective area. And then for the velocity, it is going to be 0.35 meters per second, and then the head loss for a clean bar rack screen is going to be 6.14 millimeters. And then you can also see the 50% calculations. That is running under the assumption if the bar racks get clogged, and that is with a 50% clogging, so it'll obviously take away from the efficiency rate of the bar rack, like cleaning and filtering everything out. So that's just an area to make sure to keep that everything is good and that the bar racks won't be affected and broken at all. And then I've also looked into the aerated grit chamber design. The assumed detention time is going to be 180 seconds or 3 minutes based on table 20-12 from the textbook. And then the volume of the chamber was calculated to be 35.5 meters cubed. And then using table 20-12 even further, I have some calculations and designs there that were selected. And I found the depth to be 2 meters, the width to be 2.5 meters, and then the length of the chamber to be 7.1 meters. And just a note is that per guideline requirements, the ratios for width to depth must be between 1 and 5, and the length to width ratio must be between 2.5 to 5, and those conditions were both met with the width to depth being 1.25 and the length to width being 2.84. So then we also calculated the velocity through the bottom, which is 0.204 meters per second, and then for the worst case scenario, the volume of grit was calculated to be 3.41 meters cubed per day. And then this is just table 20-12, and I kind of boxed where I was getting all those values from. And then just to point out, you can see that the length is typically between 7.5 to 27.5 meters. However, I had said that mine was calculated to be 7.1. It is a little bit lower, but because it's the typical range, we're not overly concerned yet, but that will be a factor that I am looking at and taking into consideration moving forward, making sure that's not going to affect anything. And if it is found to affect anything, then I will be going back and doing some more calculations and trying to figure out a way to get it within that range to make sure that everything's all good. So then for future work, I'm just going to continue the rest of the treatment train design and all of the components and making sure that everything is flowing well together. I will develop more of my CAD drawings and get those all finished and completed, and then also complete a cost estimate for my project. And with that, I'd like to turn it back over to Abby.
Anybody have any questions? No, that's great.
I have a question. I was waiting for other students to ask, but I have just one question for you, only one, but probably is the one that keeps you up tonight. So can you go to the elevation, structural elevation? Thank you. Yeah.
This one?
Yeah. So I see that you have distributed the lateral load on like 3 locations, 3 elevations, right? But I suppose the only diaphragm that you have is in the 3rd level, right?
Yeah,
So,
it'll be
yeah,
on
in the
top.
2nd level and 1st level, you don't have any diaphragm. It's an open space.
Yeah, it's just gonna be on the top level. I added the 3 different arrows more so for like the viewer's perspective to understand that it's going to technically hit, but it's only gonna be at the top.
Oh, so you're moving it to the top.
Yes,
Okay.
yeah.
Okay.
I had a question for Katie. Could you go to slide 21, I think? Yeah. So with the traffic coming from the upper left, there's that right turn lane.
Yes.
And then, but if you miss that, you can still turn right? Is that typical?
Within my scope, it said that one lane was a through lane and right turn lane and then an additional right turn lane. So that's, I've seen it done in real life before as
Yeah,
well.
yeah.
I know places where that exists. But that was just what was listed in my scope for what was necessary for the intersection.
Okay. And then, like, those 2 lanes, that if you turn right on the first chance or turn right on the second chance, do those eventually like merge out of the picture there? Or?
No, so both of those lanes continue all the way through to the like toll booths
Mhm.
for the Indiana Toll Road. So those lanes continue all the way.
Okay, so, like, I've seen that in person too, and I, if I'm making a right-hand turn and I take the second one, I feel like, oh, I missed it, like, so
Yeah.
I don't need to feel guilty?
No.
Or like I'm causing a traffic
No, I
danger?
know sometimes in real life there's one near my house and I'll like purposely go to the one that's on the left so then I can like skip the big line of people. I feel like I'm cheating traffic a little. Yes, Deanna.
I might be understanding the drawing wrong, but on the top, so there's that dash line, the white dash line and the white solid line, are those are supposed to be lanes for cars coming in?
Yeah, so the white dash line would be like if you're driving on a normal road that has 2 lanes in one direction, there's gonna be a white dash line in between the 2 lanes just to keep the cars separated. A solid white line usually means it's the end of the road, end of the travel way, and you don't really wanna like
Okay,
cross over
yeah.
that. And then like, if you have the yellow line, that would mean there's traffic in the opposite direction on that side of you.
This is driving recap. But, yeah, for some reason I thought that they were gonna be running into each other, because I thought they were the 2 lanes.
As long as we're in the transportation section, could you go to the roadway design criteria slide? Just for clarification, it looks to me, looking at this chart, that you have a design speed on County Road 4 of 45 miles an hour, but when you're on the toll road, you can only go 30.
That's just the entrance to the toll road.
I'm just saying you need to clarify that, because it says the toll road has a speed limit of 30 miles an hour.
Okay,
So just make it a ramp or something like that.
okay.
And then, I'm not sure which slide it was. It was the parking lot slide, I think. There. You have a 125-foot radius on all the other curves. Can the same truck make that turn with a 50-foot radius?
I got these values from the Indiana Design Manual. I need to double check with my advisor, but he told me to use those values I found for the driveway. But the 50-foot radius is also connected to the edge of the shoulder, so they will have a little more space than just 50 50-foot radius to turn in, and that roadway is 30 feet wide, so they will have space to make that turn, even if they can't like stick exactly to that innermost line.
Yeah, I can see that. You might want to look at that though. I mean, that truck, that WB67 or whatever it is, requires a certain radius for a 90-degree turn, and I think you just might want to check and see if that applies for that driveway also. And then I had a question on the wind load chart you had there. Yeah, down at the bottom, it says like 27.7 and 24.68. You know, I used to design bridges. If I calculated an ice load on a pier that came out to 27.7, I'd use 30.
Yeah.
Maybe 35 even, you know, just to get, but do you do that in buildings too, or would you actually use 27.7?
So these were just hand calculations to verify, because I'm currently working on the RISA design, and so I'm using the hand calculations and then also verifying with the software design development. So these were the ranges that are very, very, very close to what I found in the RISA design. So it's just a verification.
Okay, all right, thanks.
Any clarification on your rain garden depth? I think you may have mentioned this there, but I was, when you said the depth of the rain garden to be like a 3 to 12 feet, that's the entire depth including the media, not the ponding on the rain garden?
Correct. Yes.
Okay, just to clarify in here. And Olivia, can you go back to your like a treatment to drain flow chart? So we are on the 8th week now, you know, of the semester. So how far down the unit operations of this treatment drain? Where are you? Can you point out on the chart in here how much work is being completed?
I would say I'm around like the middle area. I've kind of been looking at all of them individually as well, just gathering information before going into the design process. And now that I have kind of gathered more of that information, I'm going through from like the beginning and making sure that everything's good.
Are you designing an equalization basin?
I believe so.
You are or not? I did not hear that.
I believe so. I
You
am
are.
blanking off the top of my head. I apologize.
So why?
Because it was listed in the schematic.
I mean, do you need one?
The way that you're phrasing it makes me feel like I don't.
Not for a warehouse facility.
I had a question about that diagram, and that I was gonna ask on Tuesday, I forget who presented it, so, but like when I look at that, the way that's labeled, it looks to me like a bar rack is part of tertiary treatment. But I always thought of like tertiary treatment as just the unit at the very end, whether that's ozonation or, so I mean, is a bar rack and a grit chamber considered tertiary treatment?
It kind of just like includes and like just extends from each of them. So the pre-treatment is like the raw sewage to equalization basin, and then the primary treatment extends down to the primary settling, and then secondary down to the secondary settling, and then tertiary down to the bottom. It is a little bit of a strange way that the chart is kind of set up in schematic, but they're separate as part of a pre-treatment instead.